Okay, so that was how we negate quantified statements. But how about when we have multiple quantifiers? What we are going to do is simple. We will just apply those two rules, the Morgan's rules for first order logic successively, again and again, until you do not have a negation sign in front of any quantifiers. Here's an example that is simple. Not for all x, there exists a y such that x times y equals 1. Okay, so what you do is look at this, switch the quantifier to existence, okay, and put the negation inside. So here you have not that exists a y, xy equals 1. Again, you have a negation in front of a quantifier. So what you do is you switch the quantifier into for all, put the negation inside, not xy equals 1. Okay, so simple as that. Now you do not have any negation in front of the quantifiers. So the result is there exists an x for all y, xy doesn't equal to 1. Okay, so this is how you negate nested quantifiers. Okay, so expressing natural language in first order logic and vice versa is quite important to make sense of statements given to us or we encounter that maybe we would like to refute or we would like to prove or we would like to make sense of, let's say. So, um, first of all, you need to be careful about the domain, as we have discussed earlier. We have the same example here. If P of x denotes x is in this room and Q of x denotes x is an engineer, then the statement every person in this room is an engineer can be expressed as for all x, P of x implies Q of x, okay, and not for all x, P of x and Q of x. Here's another example. Let's say the propositional function f of x represents that x is a fork, and s of x represents x is small, and g of x represents x is green. Okay. Now, how can we state everything is a fork? We just say for all x, f of x, everything is a fork. Okay. So here, of course, the domain is vague. We are not really interested in that, but we are interested in how to actually set up the statement in first order logic. The second one, nothing is small. Immediately you see a negation here because it starts with nothing. So if it were affirmative, it would say everything is small, but it's saying it the other way around. So it's saying nothing is small. So it's equivalently it's saying there is no small thing. Okay, so therefore this statement is negated. There exists a small thing is negated. Okay, if you actually apply the Morgan's law, you get for all x not s of x. Okay, and so that means equivalently when you want to say nothing is small, you can say everything is not small, right? um, what if you want to say all frogs are small? Now here, this you can see either as an antecedent or actually a statement related to the domain, because you are essentially saying um, if you have something that's a frog, then it is small. Okay, all frogs are small. So simply this is for all x, f of x implies s of x. Okay, something being a frog makes it small, essentially. Next one, some frogs are green. Okay, some frogs. Some indicates existence, so I'm going to use an existential quantifier here. There exists an x such that it's a frog and also it's green. Some frogs are green. I'm talking about the existence of green frogs. So how can I express this? There exists an x and that x is a frog and that x is also green. Okay, simple as that. Last one, no frogs are green. This is, if you look closely, this is the negation of that last statement. We had some frogs are green, If you negate this, you have to say no frogs are green. Okay, so it's the negation of existence. You are saying no such thing exists. Okay, so there doesn't exist, let's say, f of x and g of x, and apply the Morgan's rule here for all x, not f of x or not g of x. Simple as that. Here, this negation swaps the existential quantifier into a universal one, and the negation moves inside where you can apply the Morgan's rule. Okay, here are a couple of other examples. The sum of two positive numbers is always positive. For all xy, remember this notation. X is greater than 0 and y is greater than 0. Now this essentially together, in a way, determine my domain. Positive numbers, okay, two of them. I have two of them. X is greater than 0 and y is greater than 0. In this case, if this is satisfied, then result is x plus y is greater than 0. The sum of those two is positive. Finally, every real number except 0 has a multiplicative inverse. Every real number except 0. Again, this is sort of a domain. Therefore, I can write for all x, if x is not 0, then it has a multiplicative inverse. So a multiplicative inverse for this number exists. Now, I'm talking about existence inside a universal quantified statement. So here I have for all x, if x is not 0, then there exists a y, which is the multiplicative inverse, so x times y equals